Good morning. So, we started discussing on different models for specification, and in the last lecture we came up to this point that specification and modeling language or specification and modeling method will require it's desirable to have some features like presence of programming language elements which will enable you to specify the behavior in an elegant manner and unambiguous manner. The specification must be executable, so that we can find out whether the specification actually does what we intended. It must be readable. There will be other non-functional properties like, for example, the timing constraint. Timing constraint is not a functional property. A particular thing has to be done. Now, that has to be done within this particular time. That is an additional constraint that I am imposing on the behavior. All right. The same behavior could be a little relaxed for some other application. So, those are but the functions were the same. So, these are the non-functional properties. Now, we must have adequate model of computation. That is where we stopped in the last class. Now, what does it mean to compute? When we say we need an adequate model of representing the computation in an embedded system, what do you mean? Actually, the computation models, each computation must have an execution model. That must be that this particular behavior of the computation must be executable. Now, that computation should be, one thing is that it should be dividable into different components. The whole thing will, the whole specification, since we are talking of the hierarchy and all those, the whole system can be visualized as comprising a number of components. Now, each of these components will have their own behavior, and there should be a communication model for each of these components. Okay. That we have to specify. So, any computation model must have two things: the description of each component and how these components are combined. In other words, I can say that a model consists of a set of rules, okay, a set of rules by which I can compose the components. So, models will be, I can just say that a model will be components plus rules to compose the components. So, there are two things. One is the behavior of the components and how they connect. How they connect means again how they communicate. All right. Let us consider an example here. This is a very familiar and simple example of a dependency graph or dependence graph, where we have got 5 tasks. And the 5 tasks are dependent in this way that T2 is dependent on T1, T3 is also dependent on T1, T4 is dependent on T3, and T5 is dependent on T2 and T4. That means, say for example, T5 can start only after both T2 and T4 complete. Okay. T2 can start only after T1 completes. So, this is a dependency graph by which you can show the different components. These are the different components, task components, and there should be some communication about the completion time, that this has been completed. It can be either time that this is T2 is dependent on T1, that T2 can start only after T1 completes, or it may be also the case that T2 can only start when T1 sends a particular piece of data to T2. right. So, there can be different types of dependencies, but whatever those dependencies are, we must respect that while we synthesize. We can also add some timing information. For example, with respect to T1, this node I can say that it can start any time, but must finish within 7 units of time, that is the deadline. Okay. T2 can start at, so you can see the 2 brackets. So, it can, it's not inclusive, I mean it is not extendable, okay. 0 is included. Now, it can start any time after 1, at 1 maybe it is arriving at 1, but must complete by 8 units of time. In that way, I can also add timing constraints to each of these task graphs, timing information I would say. We can also add IO information as is being shown here, right. So, that T2 will get, now here I am not exactly showing what is the input, we are showing some token. We will come across this notion of the token, we will come across the notion of the token later on when we discuss Petri nets. Here it just shows that T2 needs some particular input to arrive in order that it can start. So, T2 needs now 2 things. One is the completion of T1 or some data to come from T1 or and the arrival of this data, input data. Okay. So, when both of them are there, T2 can start, and then like that here in T5 when it completes it will send some output data, right. So, we can show some IO information here also. We can also designate some resource sharing, like some particular resource will be shared between 2 tasks T2 and T4, right. All these we are doing in order that we can capture the dependence and what are required between, what are the constraints in the overall specification or the model of the execution. We had talked about hierarchy earlier, and here you can see that we can also use hierarchy, like I could have, instead of T1, T2, T3, T4, T5, I could have said T1, T2, T3, 4, T5, right. So, I could have combined this, and later on at a later level of hierarchy, later level of decomposition of the specification, I could have said that T3, T3, 4, this combined unit is actually T3 preceding T4. So, it is not necessary for a complex scenario I have to specify all the details at the top level. So, I can gradually come down. Now, coming about computing with the components. So, we have shown the components and some of the communication among them. So, the first is finite state machine. All of you know what finite state machine is. I will come back to finite state machines again later, but finite state machines consists of some states, and one is an initial state, one is a final state, and there are 2 functions, there is a set of inputs and some outputs, and there are 2 functions. One function is mapping from the state transition, that given a particular input, I have given a particular state. So, I can have a function, say f, which maps from the particular state x is a state, and input to the next state, where x is a set of states. Or it can be a function, could be that there is a simple state transition, it is going to a new state, okay, based on some time. Now, another function that I can have, actually this is, I will decompose, I will come back to this later, and there is another function which maps to the x and the input to the a particular output, where y is a set of outputs, possible outputs. So, all of us have seen this finite state machine, and we will come back to this again. Now, if we look at another scenario, that is a discrete event model, where which is a typical thing that we do in our computer system in a von Neumann model. Suppose we have got a queue and these are the timings. Now, if I first this part is executed, A assigned 5, so A gets 5, next B gets 7, next C gets 8, next again A gets 6, then A gets 9, so on and so forth, right. So, in that way it proceeds. That is a discrete event system, that at every level at every interval, discrete interval, some computation is taking place, and we are having a reflection of that on the memory, and that is what is known as the discrete event system. Now, most of the systems that we do, and when we program, the program is essentially in a von Neumann scenario. A program is a sequential set of sequential execution of instructions, right. So, at every step one instruction is being executed. Whenever we are trying to simulate the real life systems, often we find that some systems are not discrete, they are continuous. For example, the way the temperature changes when I heat a bath of some fluid or liquid, that is a continuous change, right. So, or say for example, actually when the car accelerates, okay. So, it is a continuous phenomenon, but we often it is a continuous phenomenon, say it takes place like this, something like this, continuous, where this is y and here is x, but we actually take some discrete views. We have discussed sampling and all those, and actually take the data at these distinct points. But in some applications, we need to actually model this continuous behavior, and for that differential equations like this is a better model. All right, all of you are familiar with differential equations. The other thing is Petri nets, okay, and Petri nets will come across in detail later. So, we can have different computation models, finite state machines, discrete level, continuous modeling. Nowadays, we are talking of hybrid systems, where we are modeling discrete behavior as well as continuous behavior in the same paradigm, and where we are using different representations, so that we can capture discrete as well as continuous behavior. I said that in order to have a complete model, we need the computation, we have to capture the model of computation, also we have to capture the communication. So, the communication, one of the very common ways which many of you are familiar with is shared memory communication. There are two computations here in two different components, and they are communicating using some shared variable, and that shared variable, whenever we call shared variable or global variable, whatever we say, that is a particular shared memory location. Please note that this is all again a shared resource that we were discussing earlier, access to the shared resource. If two computations want to write to the same shared resource, they must be mutually excluded. All those phenomena come into play here, all those issues come into play here. So, but shared memory is a nice way of communication, but there are issues of race conditions, synchronizations, etc., because it is a shared resource. That is one way. We will see each of these things in much more detail. The other is message passing. The second, so one is shared memory, the other one is message passing. Now, what is message passing? Now, message passing can be synchronous or asynchronous. Synchronous means I am sending messages at particular points of time. Let us see how it looks. Again, I am borrowing it from the slide of Professor Peter Marvidal. Here you see asynchronous message passing, that is, I can at any point of time do it, and it is a non-blocking. So, here is a receiver, here is a sender, and the sender is not caring so much about what is the status of the receiver. I will simply, this green dot is designating the computation. So, when the computation is coming progressing and coming to this send message part, it will simply send the message here. Okay. So, and this was waiting might be. So, what happens is, as you see here, this message goes over there, and as soon as it goes over there, it is just like here, it is sending it in a queue. I do not really care whether the thing, this one is consuming at the same rate or not. All right. So, this sender, as you can see in the lower figure, the sender is going on sending irrespective of looking at how many places are there in the queue. So, continuously if it goes on sending, this queue can overflow also. All right. So, then it goes to the queue, it sends. So, the other, so here it goes on sending. Consequently, what can happen, if the receiver is also fast enough, then it will go on consuming, and the whole performance of the system will be good, because the sender does not have to wait. This is called non-blocking. The other way of message passing is blocking or synchronous message passing. For example, here the sender will wait until the receiver has received a message. The receiver will receive a message, till then the sender will wait and will not progress. What will be the advantage of this? The advantage of this will be that I am sure that no message will be lost. What is the disadvantage of this? The disadvantage is that sometimes if the receiver is not fast enough, the sender will have to wait, okay, till the message can be sent. So, see here, the sender, this process comes to the send point, generates the message, sends the message, the receiver receives the message, consumes the message, and then tells the sender, sends an acknowledgement that yes, I have received it, you can progress. All right. So, you see here, this is coming over there, and this receiver is sending an acknowledgement. Consequently, if I come back to the earlier scenario here, this one, if I consider a buffer in between, all right, in the non-blocking mode, if this sender process is faster, it will go on sending and the buffer can be full. And if the buffer is full, then the messages that it is sending will not get a place and will be lost. The sender is not keeping any tag on what is the status of the messages sent. So, that will not impede the flow of the sender, okay, but we can have the buffer overflow problem, but in this case we will have no buffer overflow problem, but the performance will be reduced, because may be reduced, I will not say will be reduced, but may be reduced. Okay. So, we will be considering some models of computation here, may not be all. Plain text is of course there, that you know. We will talk about state charts, where we are classifying these based on two things. One is the computation and what is the way of communication. All right. So, the computation models say communicating finite state machines. First of all, the simplest possible is a finite state machine, and the varieties of them are, I mean, there are more sophistications. We will soon see that there are problems with finite state machines. So, we will see state charts. State charts will use shared memory communication. We will see another version of communicating finite state machines, SDL, okay, which is using message passing. We will try to see something of CAN networks, which is a data flow, but certainly we will look at Petri nets, which is looking at asynchronous message passing, and VHDL Verilog you are already familiar with to some extent. So, and C, C++, Java you are already familiar. So, this part I will not discuss, I will mostly discuss state charts, SDL, CAN networks, and Petri nets. So, next let us move to move a little further on models and specifications. So, what have we done till now? We have shown what are the requirements or desirata of a modeling language. Okay. Now, one is the model. There are two things. One are I can have different models again this and there are languages. Okay. Now, it is like a bipartite graph that there can be different models and there can be different languages, and some models can be captured by some languages, maybe L1 and L3 is powerful enough to capture this model M1, maybe L2 can capture model M2 and M3 may be captured by L4 and L3 both, all right. So, there are two things, one is the model part and what is the language in which I can represent a model. Okay. So, we will look at models here, models and architectures. We have seen now one is we are trying to get some model. We have to first capture the model. This model is actually representing the specifications and we are specifying the constraints. Now, parallelly also we decide on what architecture I want to implement this model, right. I may like to do it on a GPU, general purpose GPP, general purpose processor, or I can like to put it on a DSP architecture, whatever I want to do. Now, based on this, that is another input that I have to take. The design process is actually converting the design process is actually converting. So, what did I say? I said that when we talk of models and architectures, we start with a model and that model, from that model we derive the specification and constraints, and parallelly we need some architecture to be decided. It may be a multiprocessor unit or it may be a uniprocessor configuration, it may be a DSP, it may be a normal processor or it may be an ASIC. So, that we have to decide. Now, given this specification and constraints, the design process converts the specification and constraints to an implementation, and that implementation takes as input what architecture on which you are mapping. We also often call that specification to implementation mapping issue, which we will cover later. All right. So, given that, let us before we come to this, now we know that the simplest specification is that of natural language, right. but natural language has got its own ambiguities. So, one simple means of specification was the message sequence chart, which was later termed just as sequence charts, and which finds a place in a very popular system called UML. Okay. So, where we want to specify the use case. Here I think it is visible. Here is an example of the use case of an answering machine. Let us see what it says. The caller, on one side there are two users, one is the caller who is calling, and here is the person who owns the phone, right. He is the user. The caller calls, and for the caller the answering machine will provide what? Some welcome message, then some beep, and then the recording facility. So, these are the functions that the caller will get. What are the functions that the owner or the user will get? When he comes back home, he can play the next message that is there. He can erase the last message. He can erase all messages. He can turn answering machine on. He can turn answering machine off. There should be more. He can record new message. All right, that is not shown here. So, these are the whenever I am suppose designing an answering machine. So, this is given to me as a specification that the thing that you design must have the facility of doing all these things. Okay. Now, this is again a little too general. It just tells me these are the things you have to do. It does not tell me whether there is any dependency on these or not, whether are all these things independent, are there any timing constraints, which is following what, whether the welcome beep should be given first, or what will which of these will be played before that, etc. So, we can have a much more detailed version. Let us look at this. Say for example, the caller. What is the caller on one side and the user on the other side? The caller is calling an answering machine, and here is the phone. Now, this is a sequence chart, earlier called message sequence chart. Okay. Now, the caller first types the number, all right. The phone gets that and signals the call. The answering machine waits and signals pick up. Some time has elapsed, no one has picked up. Now, while I describe this, the horizontal direction where this mouse pointer is moving is the space, and the vertical direction, this is the time. All right. So, it waits for some time, and then the answering machine sends the announcement to the phone. The caller gets the announcement. Just you see the delay, very little delay. Okay. Then it sends a beep. The answering machine sends a beep. Subsequently, look at this small delay. The phone sends the beep to the caller. The caller sends the message. The message is transmitted with little delay to the answering machine, and returns the caller, returns the handset, that means ends the call, and the phone is answering, end of call to the answering machine is stopping. So, here we are, but still there are much more details on this. There are much more details on this, because might be suppose the beep has been sent and the message, the user was just remaining silent, not sending any message, then beyond a particular time the answering machine should again send a beep and stop. Okay. All those details are not shown here, So, there are, so it is a sequential flow that has been shown. There are multiple sequences, conditionalities, which is not shown here. But this is one way, and there are commercial tools available using which we can use those tools to specify using message charts or sequence charts. So, here is another message sequence chart taken from Germany. Here is the time, and it is showing, you see, there are cities and trains are traveling from different cities to another. So, from Cologne a train starts, okay, it is in Cologne, this space, it is waiting in Cologne for a while, it starts and takes the time, some time to come to Aachen, another city. It waits in Aachen for a while and then travels to Amsterdam. Okay. See, the train is quite fast, because from what can we understand whether the train is fast or not? From the slope of this curve. If the curve is, I mean, thus if it is much more drooping, in that case it is slow. The more horizontal it is, the faster it is. So, it is quite fast that it travelled from, oh sorry, it did not travel from Aachen to Amsterdam, it went to Brussels. Okay. There it stopped for a while and went to Paris, waited in Paris for a while, longer time, then travelled back to Brussels and back this. In the meanwhile, another train, there was a shuttle train from Amsterdam to Brussels. Now, so here it is coming here, right, and there is a train from Paris to this. So, we could represent this, but what is the problem? One problem is that I cannot, suppose the scenario is this, that this train starts from Cologne, comes to Brussels, and this shuttle train comes from Amsterdam to Brussels, and then these two join together, the coaches join together and travel to Paris. Whether that is happening or not, what is happening here, that is not shown, these are very distinct. So, whether these are synchronizing, that people are just synchronizing here, or there is an accidental overlap, that is not very clear in these representations. Timing. This lecture I will conclude with this explanation of this timing. You see the timing here in UML. In UML, where we can specify this using message charts, what are the ways we can specify timing? It is not integrated in the representation. We have to separately show the integration. Here is a very interesting example. Say, just as I am recording the lecture, so, and there are some recording assistants sitting in the other room who are recording. What are their time of engagements? The professor has got many other duties, administrative duties, and he is doing that, all right. And all of a sudden, now you see this is the time now, okay, this is the time. So, all of a sudden he finds that, well, there is a class, so he has to immediately switch his action, come to the preparation mode, spends preparation for some time, and then comes to the lecture. The lecture takes the least amount of time. So, we provide the lecture and again rush for some other administrative work or some other work might be. Lots of works are kept pending. So, those are done. So, this is the timing which a professor is spending, all right. So much time for the teaching, so much time for preparation. Maybe for this lecture the preparation time was less, okay, than this one. What is happening to the recording assistant on the other hand? They are also doing other duties, all right, and then when the teaching is coming up, they are immediately leaving their other duties and coming to recording. And after recording, when the professor is doing some other tasks, they are busy doing the editing, and they finish the editing and then go back to this other duties. So, in this way we can represent the timing of both the, more than one processes, and it is up to the design system to look at these timings and adhere to these timings. Okay. So, we will start from we will follow up in the next lecture from this. UML is one method of representation, but we will now look at finite state machines and other versions extensions of finite state machines from the next lecture.